All right, so we get started. Hope everybody's doing well. Any questions? I just sent back the scores on homework 3. So you guys just turned in homework 4. Pretty soon I will post homework 5. Let's see. Yeah, hope everybody had a good break. Okay. So luckily we ended up at a relatively reasonable stopping place last time. And so now we can start with a new topic, very important one, which is fiber product. So now a very common thing that happens in lots of nice categories, geometric categories, is that I can take X and Y in my category and I can take their Cartesian product and it will give me the same thing. And in categorical terms, this is a product in the sense that there are projection maps to X and Y. And if I have a map of X and Y into some third thing W, then I keep doing this the wrong direction. If I have W mapping into X and Y, then just taking ordered pairs gives me a map into here. So obviously, this is the sort of thing we'd like to do with schemes. We'd like to say something like A1 times A1 is A2, right? This is a manifestly obvious fact. But if you interpret this as Cartesian product, it's a manifestly, obviously wrong fact. Cartesian product of A1 and A1 is absolutely not A2. A2 has a bunch of points that aren't products. They come from irreducible one-dimensional subvarieties. No, it's not true as sets. That was exactly what I was saying. In here, there's a point called f of xy for a random irreducible polynomial. That's not, what are the points here that correspond to that? Right. So when I write A1, there's an underlying topological space. It is not true. This is not a true fact about, it's a true fact now that I wrote not equal to, because there are points here that don't come from an ordered pair of points here. Right? There are prime ideals in C of xy that don't come from a prime ideal in C of x and a prime ideal in C of y. That's one way to get a prime ideal in here, right? I could take an irreducible polynomial in x and an irreducible polynomial in y and look at the ideal they generate, but that's going to miss most of the interesting subvarieties, right? So the point is now this guy is a point, right? There's a generic point of this, weird squiggly thing, which is the solutions to this polynomial, and that's not coming from points here. Okay, so when we think about schemes, we can't naively take Cartesian product. Now there's an upgrade of this notion of Cartesian product, which is usually called pullback or fiber product, which is if I have X and Y and they map to a common Z, then I can look at all the W's that have maps to X and Y and Z that are compatible. And the sort of universal thing that fits into this is what's called fiber product. So fiber product is the initial object. The fiber product is written like this with X and Y and Z on here, such that I have a W, it maps into X, it maps into Y, and then this diagram commutes. Sorry? It's term? Oh, it is terminal. Shoot, yeah, you're right. Sorry. It's always counterintuitive. Anyways, right, it's because things that are defined by mapping into stuff tend to be terminal because other stuff maps into them. And I should be careful not to get those crosswise, but yes, it's terminal. Right, it's a limit, not a colimit. Okay, great. Yeah, another way to say this would be, it would be the limit of this diagram, if you like to think about things in terms of limits. All right, so this is a notion that makes sense in any category. We'll also call this pullback. That's the more common kind of general categorical term, that this fiber product is the pullback of this diagram. In algebraic geometry, we usually call them fiber products. Now, in many categories, this is easy to define. So for example, in sets, I guess I should write in set. I can just call this map alpha and this map beta. And then the fiber product is literally just going to be a subset of the Cartesian product. It's the x and y, such that alpha of x equals beta of y. And this works in most categories where you have sets with extra structure. So for example, it also works in topological spaces, where I just give this the subspace topology. It works in groups. So you can check if X, Y, and Z are groups, and these are group homomorphisms, then this is a subgroup of the Cartesian product, etc. But we sort of see immediately here that it's maybe not going to work super well for schemes. And there's sort of another obvious point with schemes. So this construction actually works in the category of ringed spaces. So if X and Y are ring spaces, X, Y, and Z are ring spaces, then there's a natural way to define this fiber product, where I can take this usual definition, and then what's the structure sheaf on this going to be? Where if I take this guy, so when I say this guy has the subspace topology, I mean that it has a basis that's given by the fiber product of open sets in X and open sets in Y. So I only need to tell you what I get when I'm taking the fiber product of U and V. And there's an obvious sort of guess for what I should have. I should have a ring, because I have a map to X, right? I have a pullback map on functions from X. Because I have a map to Y, I have a pullback function on maps to Y. And that's going to have the property that if I pull back functions from Z, then those are going to have to, yeah, sorry. Right, that the map on functions goes the other way. Right, so the sort of obvious guess to put here is something I take functions on O of U and O of V, but then I have to somehow account for this Z here. So I'm going to be a little bit sloppy here. want to take O of X evaluated on. And I'm going to be a little vague about what subset of Z I want to take here. It doesn't really matter that much for my purposes. But the point is I'm taking a tensor product because if I have a function on Z and I pull it back to X and I pull it back to Y, then that should have the same image here. Right? The reason I get this is that tensor product is the opposite of a pullback. It's a push out. It's a fiber coproduct in the category of rings. So if I have two maps of rings, C goes to A, C goes to B, let's say commutative rings to make my life easier, the unique thing I can put here is the tensor product of algebras, A tensored with B over C. And if I had a third algebra, D, where I had a map of B of that and a map of A into that agreed when I restricted to C, then I would get an induced map here. Yeah. Because I want something that maps into both of these, right? I can't take something on the intersection and pull it back to here, right? Functions restrict. So I want something that maps in here and it maps in here. So probably I shouldn't assume that this is open and I should take a co-limit over opens containing it. Right, I'm really what I'm tensoring over is the pullback sheaf from X to here, from Z to here, which is the same if I do it either way. Okay, but let's not worry about that. Because we're not going to use this as a definition. This is just kind of like if you were thinking abstractly about ring spaces, this would be a reasonable thing to do. But it doesn't send schemes to schemes. And so it's no good. Okay, so this is a perfectly sensible thing to do in ring spaces. You could check this as a coproduct, but doesn't send schemes to schemes. And just to give you sort of a flavor of why this is a problem, like why doesn't this send schemes to schemes? Right, what could I do? I could take spec of C mapping to spec of R and spec of C mapping to spec of R. So this means think of C as an R algebra. And then what would I get here if I took this product of ring spaces? I would get 1 point. This is 1 point. This is 1 point. This is 1 point. And my functions on that 1 point would be C tensored over R with C. And maybe you've seen this before, maybe you haven't. The way you should think about this is I'm thinking of C as an R algebra. So I think of C as R adjoint X mod X squared plus 1. And then what happens when I tensor with C? I get C tensored over R with C. That's C of X mod X squared plus 1, which is isomorphic to 2 copies of C. So one way to think about this is this sort of comes from the fact that if I think of C as an R algebra, it has a non-trivial automorphism. So there's 2 maximal ideals in this guy, one of which comes from mapping both copies of C to C in the usual way, one of which comes from mapping it as C tensor R to C. So I can map this to A tensor B goes to AB as complex multiplication, or I can map it to A times B conjugate. Yeah. Yeah. I mean, if I have an algebra D, right, and I have a homomorphism from B and a homomorphism from A, and they agree on C, right, then that means, so let me call this homomorphism A and this homomorphism. Oh no, that's bad. No, 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 don't do that. Let's call this homomorphism N and this one N. Then I can define a homomorphism that sends A tensor B maps to M of B times N of A, right? And if I had something in C, I could move it from one side to the other because on C, M and N agree, right? So you can think of this as the definition of tensor product of algebras. It's this sort of interesting thing that, tensor product, you can think of it as just this operation on modules, but then when the modules have extra structure, that sort of carries over, right? So this is the usual tensor product as C modules, but because A and B have commutative ring structures, the tensor product inherits a commutative ring structure. Yeah. Yeah. I mean, that's a special case and another way that I think maybe you could kind of see these issues. Um, I don't know if that's sort of the intuition I would think about. Let me finish my example and then I'll try to come back to this. Um, all right. So here, this guy is not a scheme. Why is it not a scheme? Well, because if I took spec of this guy, it would have 2 points. Right? I have this function ring, but I know the answer I'm supposed to get is 2 points, each of which is a copy of spec C. Right? And spec of this guy, it doesn't have 1 point, it has 2 points. So this is just, kind of one of these weird manifestations. So I think maybe a better way of answering what you were coming to, which I don't know if it's that helpful, but we'll see. So why is it that in set and topological spaces and groups, we can do this? The reason is, well, this isn't true in groups, but in set and in topological spaces, you can interpret the underlying subset of the space as a Hom space in the category. So in set, there's an object called point, and the underlying set of a set is the same as Hom from point into that set. So X is equal to Hom of sets of point into. So what this pullback property exactly tells me is that if I look at Hom of the fiber product into something, what is into some W? Well, that's the same as taking the fiber product as sets of from X into W, of Y into W, right? If I have a Hom from this fiber product, it gives me a map from X and a map from Y. And I'm taking the fiber product as sets over of Z into W, right? So I'm looking for of X to Y to W, of Y to W, such that they agree on Z. So this is the fiber product as sets. So in a category where you can interpret the underlying set as Hom from an object, right? So that's true in set, but it's also true in topological spaces. In topological spaces, there's a topological space called the point. It's only got one topology because there's only one possibility. And the points of the topological space are Hom from that point. So I have to get this description of it in any category where I can do that. And in schemes, that's not true. The points of a scheme are not Hom from any fixed scheme. Yeah. This equality? Because for every element of X, I have a Hom that sends the point to that element of X. This equality. This is just another way of saying the universal property. Shit. Yes, you're right. I told you I was going to get this backwards. It's all backwards. Yes, I'm sorry. Okay, sorry. Yeah, now this is correct. This is just restating the universal property that Hom from W into this fiber product is the same thing as a Hom into X and a Hom into Y that agree on Z. Yeah, cool. This is literally restating the universal property, right? Like it says that having a Hom in here is the same as having an alpha in here and a beta in here, such that when I compose, yeah, I shouldn't have called those alpha and beta. Sorry. Having a gamma and a delta, such that when I compose this guy with alpha and this guy with beta, they're equal. Yeah, this is fiber product as sets. I'm thinking of these Hom spaces as sets. There would probably be some fancier way to do this if you were in rich category, yada, yada, yada. But I'm thinking of these as sets. So the exact problem here is this point of A2 comes from the fraction field of the curve that satisfies this, right? And so there's a point of A1 over that fraction field and a point of A1 over that fraction field whose product corresponds to this point. But this one is an actual point of the scheme as a topological space, and these ones are. So in this sort of language of W points of schemes, right, I could rewrite this as take X, Y, look at the W points of that, and that's the fiber product as a set of the W points of X with the W points of Y over the W points of Z. And these are all as sets. This is as sets. But this is, at the moment, this is just sort of categorical fiber. Okay. So, well, do these fiber products actually exist in schemes? So a fiber product, if it existed, would be an object satisfying this property, but it's not obvious that there is a well-defined scheme, X times Y over Z. Yeah. Does this hold in the kind of scheme? Why does what hold this? Yeah. This is just a restatement of the mapping property. Like literally, this is defined to be this. 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 I'm just writing the line above in different notation. Right. As I was saying here, right, what if I wanted to think of this point of the scheme as a point in the sense of a mapping, right? Think about what its residue field is. Its residue field is the fraction field of C of xy over f of xy, right? So this is a domain. I take its fraction field, that has an obvious map from C of xy. That's the point, the generic point of this guy, this curve, right? And then, well, how would I think of that as a product of points in A1? Well, it would be a point in A1 over this field, right? So it would be a Hom from a point of the fraction field of a point of A1 in here. And what would those be? Well, it would be the map from rational functions on X into here, rational functions on Y into here. Assuming this guy was generic enough, right? If I project this down to the x-axis or project it down to the y-axis, that's what this means. Then I get a point in A1, but a point over this field, which I don't think of as a point of my scheme. Right? It's instead sort of a rational parametrization of this curve by using the x value or the y value. Okay. So enough abstract categorical stuff. Do these guys exist or not? They do. So theorem, this fiber product exists. Now there's a long discussion about this in Wachtell. I don't want to go through kind of a careful proof, because you can read it in the book if you want to. I think the underlying concept isn't that bad. So the first question is, well, what if X, Y, and Z are affine? Then I've already answered this question, right? The category of affine schemes is the opposite of the category of rings. So pullback in the category of affine schemes would be turned into push out in the category of rings, and we've already discussed that. That's tensor product. So almost by definition, if I take spec of A and spec of B, and I take spec of C, then this fiber product is isomorphic to spec of A tensored with B over C. So the only real content in this theorem is if I take two schemes and I write them as a union of affine things, can I take the fiber product of the affine guys over affine guys and glue those all together in a consistent way? And the answer is yes. It's a little bit of work to convince yourself that you can. There's sort of a fancy categorical way of thinking about this that Wachtell discusses. And there's also a like very hands-on, like, okay, well, think about the case where Z is an open set of an affine guy. Think about the case where, so Wachtell, I mean, it's like maybe 8 or 9 steps of making X and Y like a little bit more general. But the moral is really just, so a useful way to think about this is Z has an open affine cover. So I can cover Z with affines, and I can take their pre-images in X and Y. So this guy should be covered by the pre-images. So then I can assume that Z is affine by just looking at the pre-images of the affine subsets of Z and doing the fiber product over those and then gluing all of those together. So assume Z is affine. And then, well, I can take X and Y as covered by affine guys. And if I take all the pairs of those, I'll now have 2 affines mapping to an affine, and I know what to do. I take affine covers of X and Y, and then I take tensor products pairwise. And of course, you should be a little suspicious, right? It basically takes Vakil like 2 or 3 pages to sort of explain, at least to his satisfaction, why this is a consistent thing to do, right? I'm making a bunch of choices, and you should be suspicious that what I'm doing is independent of all those choices. But it's actually not so bad because we know that the sort of categorical property implies uniqueness. So if I can show that any object with this property exists, then I will already know that it's unique up to unique isomorphism. So what I'm sort of always using here is that morphisms of schemes are compatible with gluing, right? Morphism of schemes is always enough to tell you what it is on an open cover and make sure that they agree on the overlaps. So this is kind of the moral story. And if you want the details, you can read Vakil either for the very hands-on, like, okay, now assume that this guy is an open subset of an affine kind of proof, or there's sort of a more fancy categorical one where you sort of think about, he's sort of concealing this a little bit, but you can prove that something is that a functor on the category of rings or the category of schemes is hung into a scheme using abstract properties of the functor. And so kind of the more fancy way to do this is to say, oh, I can think about this as a functor on W and prove it has the properties I need for it to be hung into a scheme. Sorry? Well, no, not everyone is. But you can sort of say the properties of being a scheme more abstractly in terms of the functor. So, you could define schemes to be functors from the opposite category of rings to sets satisfying yada, yada, yada properties. And then it's sort of a more categorical thing to be like, well, I know what it means to take the fiber product of 2 of those functors. When I do that, is the result I get again a scheme? All right. So why talk about this fiber product stuff? Because it's actually really, really, really important. You use this operation all the time. And actually, we've secretly been using it for a while. So many important constructions, some of which we've already done, are in fact fiber products. So for example, if alpha from X to Z is an open inclusion, then what happens when I take the fiber product of X over Z with some Y? So I'm looking for something where, right, I have my W mapping into Y. And what does the fact that it also factors through X tell me? It tells me that when I take Y and I do this composition, the image lands in X. So this must have mapped into the pre-image. So when I take this fiber product, it's exactly just beta inverse of X. So it's taking the pre-image of an open subset of the target. And that's again an open subset because the map is continuous. So this is telling us that fiber product preserves open inclusions. this seems as good a point as any to say you'd actually be more likely to hear this statement with a different word for fiber product, which is base change. So a common thing that happens is we are thinking of X as a Z scheme, and then we have some Y mapping into X. So we're thinking of Z as a base, and X as some kind of family over it. And then when we take fiber product, here we get a Y scheme whose fibers are essentially the fibers of Z. So this is pulling back the family. We often call this, when we sort of want to focus on this map as a structure map and then think about this map as a structure map, we call that base change. Yeah. Yes. Similarly for closed inclusions. And the way to think about this is a closed inclusion of affine schemes comes from the map of A to A mod I. So when I do my fiber product, what am I doing? I'm tensoring with B. So then this maps to the tensor product, right? If I tensor product the ideal with B, I'll get an ideal of the tensor product. And so I get closed inclusion. All right, cool. So yeah, one important note here is if X and Y, or I should say alpha and beta, are both open or both closed, then you get the intersection. The intersection of two open embedding two open subsets is open. The intersection of two closed subschemes is closed. But we had talked about what it meant to intersect two closed subschemes. This is sort of the easy way to do it, to just say, oh, you take the fiber product. Yeah. The reason it's called base change is very often we want to think about not schemes on their own, but schemes with structure maps. And so in this case, I would be thinking of X going to Z as the structure map. And so Z would be called the base. I'm thinking of this as actually, this is like a family. I'm interested in the fibers of this map. Sorry? Well, so, I mean, I can think, I mean, this is just an example, right? So, when I say base change preserves open inclusions, what do I mean? I mean, if this map is an open inclusion, this map is an open inclusion. So base change and fiber product mean the same thing, but fiber product means that you're focusing on the spaces, and base change means you're focusing on the transition from this map to this one. That before I had a map over one base, and now I have a map over a new one. So another kind of important example of this, right, is if I have an A scheme, which, as you'll recall, is the generalization of spec of an A algebra, then one thing I might want to do, right, is I might want to take some other algebra mapping here, spec B, right, and do the base change. So you'll often see this written as the fiber product over A. We often don't bother to write spec A, and we just write A. Spec B. And of course, if X is spec of some A algebra A prime, then this base change just means I change my coefficients. Is spec of B tensored over A with A prime. So for example, if A prime is, A adjoin a polynomial mod some polynomial, right? Then this tensor product B prime corresponds to the same equation, but now with coefficients in B. So we saw that exactly here. Right? That C is about thinking over R and thinking about solutions to x squared plus 1. And then when I base change, well, now I'm looking at solutions to that over C instead of over R. All right. So for me, at least, one of the really important interpretations of schemes is they give you an object that sort of tells you about solutions to an equation over a ring. And one example of base change is you're changing the underlying ring. So for example, right, like the sort of thing you might want to do is take an equation with integer coefficients and look at its solutions over Z, look at its solutions over C, look at its solutions over FP. And then a natural thing to be doing would be to be thinking about spec Z here, and then think about spec C here. Right? This is a very kind of common thing to do. So for example, one very common piece of terminology is that for any scheme, X, I can look at ANX. So what is this? This is over every point in X, I put an n-dimensional affine space. And I can say this more precisely by saying I take X, and then I take the fiber product over Z, which you'll remember means over spec Z, with spec of ZX1 up through Xn. So if X equals spec A, then this is just spec of polynomials and n variables in A. So as often happens with schemes, if you're thinking about what's actually happening as a set here, it's some really crazy stuff. But if you just think about the functions, it's the obvious thing you would do. What is affine space? Oh, you add n variables, and you just let them take any value you want. Yes, this is the definition. Or at least a definition that people would often use. We had defined this when X is spec of A before as spec of the polynomial ring with values in A, but this makes sense for any scheme. And what am I doing? Oh, well, I'm covering X with affines. For every one of those affines, I'm thinking of that as spec of A. I'm adjoining n variables to that, and I'm taking spec of that polynomial ring, and then I'm gluing them back together. And fiber product is just a convenient way of not saying, of just saying, oh, let me push that all into the box of this theorem that says fiber product exists. Right? If I want to think about this, I should still kind of unpack it that way. But I don't have to sort of separately prove that this guy exists. Or for example, right, another thing that people often want to consider would be Tn of x, right? And again, that's I take x, I take the product over z, but now instead of spec, I put proj of zx0 up through x. And again, what does this mean? This means locally I cover x with affines. For each of those affines, I look at proj of that ring adjoin n plus 1 variables, and then I glue them all together. Right? But I don't have to actually say that. That's all built into the definition of fiber product. Yeah. Why are we using what? Because that's the initial object in the category of rings. Right, because this gives us the right definition for any algebra A. A tensored over Z with Z adjoin x1 up through xn is A adjoin x1 up through xn. Yes. Every ring is a Z algebra in a canonical way. And so I can think of every scheme as a Z, as a spec Z scheme in a canonical way. So, right, if I were going to sort of draw the picture here, I would have X. It would be mapping to spec Z. This is sort of the relative way of thinking about a scheme if you don't want to do anything relative. And then I would say, oh, over spec Z, I have, AN Z, and then this fiber product is X. Right. So one of the sort of interesting things about this base change story is, of course, there are always two ways to think of a fiber product as a base change. I can think, well, my basic object here is n-dimensional affine space sitting over spec Z. So what am I doing? I'm base changing. So now my X is the base, and I'm putting a family over that where every fiber is an n-dimensional affine space. But it's going to be kind of weird, right? Like over, because points in X can have different residue fields. So it's like over a point with a given residue field, I'm getting a copy of n-dimensional affine space over that field. And I'm sort of, taking the AN over spec Z and sort of spreading that out with X as the base. But I could also think about, like, here's AN, here's spec Z as my base. Now I'm taking my sort of AN as the base, and this guy is a fiber over it. This guy is sort of and again, every fiber, well, it's not quite going to be X, right? Like morally, you would think the fiber of this would be X, that this is just kind of a Cartesian product. But schemes are weird. So you get like, base changes of X over different fields, right? Because there are points in AN of Z. And what does that mean? That means a prime ideal in here, right? And so, for example, any finite field can be written as a quotient of this guy. That defines a point in here. There's a fiber of it over here, and it's going to be sort of something different. It's going to be like, X base change to that finite field. Yeah. We have a complete classification of the prime ideals in there. No, because they're right. I mean, any finitely generated domain, right? You're forgetting about the generic. right? So there are lots of finitely generated domains because the maximal ideals in here correspond to finite fields and elements of those finite fields, right? But there are non-maximal prime ideals, lots of them. And those might have characteristic zero fraction fields. The first example being, a Q is the fraction field of Z. But again, if I have any complex variety, which is defined by integer equations, I can mod out by those integer equations, and I get a characteristic zero field, a characteristic zero ring, whose fraction field is something over Q, right? It's basically the Q solutions to those equations. All right, cool. I'm probably completely out of time. Oh, yeah, I'm completely out of time. All right. Well, that's as much as we were going to get to say about fiber product today then. All right. See you all on Wednesday.